So today we're going to look at proofs by mathematical induction, and we're going to look at this question here, which is a fairly standard typical one. We have f of x equals the square root of 1 plus x. First of all, we have to show what the second derivative is, and then we have to use induction to prove this. These mathematical induction questions tend to follow exactly the same methodology, so they're well worth getting to grips with. This one, for example, was worth 4% of the entire IB, HL, AA mark. You were given around 13 minutes to complete it. So let's have a go. Okay, right, so first of all, we have that f of x equals the square root of 1 plus x, which is 1 plus x to the half. Therefore, f dashed of x is equal to half 1 add x to the minus half, and f dash dashed of x equals minus a quarter 1 add x to the minus 3 over 2, which, putting it in the form that they want us to put it in here, is minus a quarter times 1 over, that bit there is the square root of 1 plus x, and that bit there is cubed, which is this answer here. Okay, now we have to use induction, and basically the methodology we use is the same for all induction. First of all, A, you have to prove it for the base case. Now the base case in this particular example is n equals 2. That's the lowest case. So we need to prove that this formula here is correct for n equals 2. And all we need to do that is just put in n equals 2. So let's put in equals n equals 2. So f2x, which is equal to f dash dash x, putting n equals 2 into this formula here, equals minus 1 quarter to the power of 2 take away 1 times by 2 times 2 take away 3 factorial over 2 take away 2 factorial times by 1 add x to the power of a half take away 2. Okay, and let's just simplify that. That gives us minus a quarter to the power of 1, which is minus a quarter, times 1 factorial over 0 factorial, well that's just 1, times by 1 add x to the minus 3 over 2, which equals minus 1 over 4 square root of 1 add x cubed, whoops, my apologies, which is the same as f dash dash x. So we have proved that for the base case, n equals 2, the general formula for n works. Okay, but that's only part of it. So next what we got to do, and we have to write this, you must write this, assume true for n equals k. You must write this. If you don't write this, you lose a mark. So we have to assume that it's true for n equals k, and therefore, as it's true for n equals k, we can assume that our formula fkx, which equals minus a quarter to the k minus 1, 2k minus 3 factorial over k minus 2 factorial times 1 add x to the half minus k is true. We can assume that that is true. Okay, so now what we need to do, C, what we need to do is we must show that for replacing k by k plus 1, we must show therefore that f k plus 1 x equals minus 1 quarter to the power of k plus 1 minus 1. All we're doing is replacing k by k plus 1 factorial over k plus 1 minus 2 factorial times 1 add x to the minus half minus k add 1. Sorry, I haven't got a lot of space there. So what we've done is we've said that we need to show that, now let's just tidy that up a little bit. We must show therefore that f k plus 1 x equals minus a quarter to the power of k times by 2k minus 1, just sorting that one out there, factorial over k minus 1 factorial times by 1 add x to the minus half minus k minus 1. So we must show that this is true. Okay, assuming that this is true. Okay, now what we're going to do now is we are going to differentiate this, which we've assumed to be true, and then we have to manipulate it in order to get it in the form like this. Now let's just change colour just for a sec, because pretty much the way that you do this you can sort of see by looking at the kth derivative here and looking at the k plus 1. Okay, we got a minus a quarter to the k minus 1 here, and we got a minus a quarter to the k here. Somewhere we are going to have to multiply by minus a quarter, so we want to be looking out for that. Also here we have 2k minus 3 factorial, and here we have 2k minus 1 factorial, which means somewhere we are going to have to multiply by 2k minus 2, 2k minus 1 on the top, and on the bottom we have k minus 2 factorial, and it's got to convert to k minus 1 factorial, which means on the bottom somehow we have to multiply by k minus 1. We just have to be looking out for these, and this will give us the guidance as to how we proceed. Okay, so let's go back into our black pen. Okay, so D, let's do it now. So basically we have to differentiate this, remembering that all of this lot here is just a constant. So our differential f to the k plus 1 x, this is differentiating f to the kx, equals, okay, so it's minus a quarter to the k minus 1, 2k minus 3 factorial over k minus 2 factorial times, right, this is the only bit that we differentiate here, which is 1 plus x to the minus half minus k. Well, that will be minus a half minus half minus k times by 1 plus x to the half minus k minus 1. All we've done is just differentiated that by moving that down and taking the power down by 1. So we can see that we already have 1 plus x to the power of minus half minus k minus 1. So all we need to do is manipulate this bit to get in this form. Okay, so basically let's have a look at that. So that equals, okay, minus a quarter to the power of k minus 1 times by 2k minus 3 factorial over k minus 2 factorial. Okay, now clearly this is the bit where we're going to be manipulating in order to get our terms in the right form. So let's write that as 1 minus 2k over 2 times 1 add x to the half minus k minus 1. Okay, now 1 minus 2k over 2, because we know that we are going to have to multiply somewhere by minus a quarter in order to get that from minus a quarter to the k minus 1 to minus a quarter to the k, let's multiply top and bottom here, multiply that by 2, and multiply this top and bottom by 2, which here gives us our 4. And if we flip this around as well, that gives us our minus a quarter. So we can rewrite that as minus a quarter times minus a quarter to the k minus 1 times by 2k minus 3 factorial over k minus 2 factorial times by 2k minus 1 over the minus a quarter we have now moved out there times by 1 add x to the half minus k minus 1. Okay, now all we need to do now is have a look at this here. Well, let's add in, because we know that we need to get a k minus 1 on the bottom. So let's multiply. So this becomes minus a quarter to the k. So we've got that bit sorted out. That's what we needed to do. If we look up here, we needed to get that bit sorted out up here. So we got minus a quarter to the k. Now we just need to do this. Let's times by 2k minus 3 factorial over k minus 2 factorial. Okay, let's have a look at this. Now what we need here is 2k minus 1. Let's multiply top and bottom by k minus 1. And the reason we're doing that is in order to get this bit here into k minus 1 factorial, which is what we need, times 1 add x to the half minus k minus 1. Okay, we need to go on the next page here. Okay, and basically now what we do, we're almost there. That equals minus a quarter to the power of k times by 2k minus 3 factorial over k minus 2 factorial times k minus 1, so here will be our k minus 1 factorial, times by k minus 1 times by 2, which is going to give us 2k minus 2, that's the 2 times the k minus 1 is 2k minus 2, times by 2k minus 1, and you can see it's all fitting into place here, times by 1 plus x to the half minus k minus 1, and 2k minus 3 factorial times 2k minus 2 times 2k minus 1 is 2k minus 1 factorial, and k minus 2 factorial times k minus 1 is k minus 1 factorial times by 1 add x to the half minus k minus 1, which is what we seek, and therefore that is what's required, and therefore we have proved that if it's true for n equals k, we assume it's true for n equals k, then we had to show this, which we have just done now. We've just shown that here. Therefore we write as required. And now this is most important. At the bottom, once you've done all the work, don't throw away the final mark. You have to write this. Hence, as it's true for n equals 2, which you've already proved, which was the base case, and as it's true for n equals k plus 1, assuming true for n equals k, then the statement is true for n greater than or equal to 2 by mathematical induction. If you don't write this bit at the bottom and you don't write it in this way, then you lose a mark. So you can have done all the work and you lose a mark at the end just for not basically writing the conclusion. That basically is it. We've now proved by mathematical induction this, and we should have got pretty much full marks on that. So I hope you found this useful. We're going to do some more of these and stick them in a podcast. So if you've enjoyed this video and found it useful, please like it and subscribe to the Gresti Academy YouTube channel. Thank you.